What is this Cayley's formula? It is a formula for counting. Cayley's formula, first let me write down what is the statement. So it says that the number of labeled trees so I'm writing here, I hope everyone can see the number of labeled trees on n vertices is n to the power of n minus 2. This is the statement. Okay, so this is the one that we are going to discuss through the talk. What is the meaning of it? I'll start by explaining. Maybe everyone knows, or I don't know, since I don't know whether everyone knows. So let me explain what this is. So what is a graph? What is a so a graph? So a graph in general, it is first it will be a finite graph always. So finite graph will have some vertices, finite number of vertices, and some edges. Edges means connecting two vertices. So this is, for example, a finite graph. Okay. So where always we will take the vertices as labeled. Okay. 1, 2, 3, 4, and 5. Okay. In this case, 5. So these edges, this is a purely combinatorial one. It's nice to draw pictures, but one should not mistake it for the geometric picture here. It just means there are 5 vertices, 1, 2, 3, 4, and 5. 1 and 2 are connected to each other, 2 and 3 are connected to each other, 1 and 3 are connected to each other, 2 and 4, 3 and 4 are connected to each other, 5 is not connected to anyone else. So it is often just the vertex set is, there are 2, 1, 2, 3, 4, and 5 in this case. And the edge set, what is the edge set? If you want a formal definition, it is a symmetric relation on the set of vertices. Okay. So where for now I don't allow a vertex to be related to itself. Maybe it's not reflexive. So for example, here 1, 2 is an edge. It's an undirected graph. So directed graph is another concept where we can allow this to be tuples. But here 1, 2, 1, 3, 2, 4, 2, 3, 2, 4, they're all edges. And then 3, 4 is also an edge. I think I covered all the edges, right? So yeah, 2 to 4. Yeah, I think I got all the edges. So these are all the edges in this graph. So that's what a graph is. And how many graphs are there is very simple. So there are, so with n vertices, there are 2 to the n choose 2 different graphs. On vertex set n. So when I write the square bracket n, I mean the set 1, 2, 3 up to n. Okay, so how many graphs are there with vertex set 1 to n? This is this. Here itself, there is an important point. So in counting these things, in all counting problems, one has to be clear what we are regarding as same and what we are regarding as different. For example, so when I write this 2 to the n choose 2, so for example, the following two graphs are actually different. I regard them as, so if I have 1, 2, and 3, and 1, 3, and 2, they are not the same. Okay, so they are not the same. And because the vertex labeling is important. So here 2 has 2 neighbors, 1 and 3, whereas here 2 has only 1 neighbor. So they are not the same graph. But you may see that as pictures, they are exactly the same. But that's the question. What are we counting? When we are counting, we have to be clear about what things we regard as same, what things we regard as different. And here it is very important that everywhere I am going to be looking at labeled ones. So that means if the labeling is different, they can be different. On the other hand, one should be also clear that if I write 1, 3, and 2, these are actually the same. there is no difference between the first graph and the second graph, because in both of them vertex it is 1, 2, 3 and edges are 1, 2 and 2, 3. Okay, so what are same, what are different, what should be clear. So these two are same, but these two are not the same. Okay, so that is how we are going to be when we are counting trees also. So now I have described for you what a graph is, possibly unnecessarily, but who knows. Now let me describe what is a tree. Tree is a connected graph with no cycles. So I have used terms which I will explain in words. So a tree is a connected graph with no cycles. For example, this graph here, the one that I first drew, that one is not a connected graph. Okay, so if you look at this graph, sorry, what did I? If I look at this graph, this is not a connected graph because 5 you cannot go from. So what is connected? Let's just describe it informally. The concept is very clear. Here 5 is disconnected from everyone else. You cannot go from 5 to anywhere else. Now it's not that you have to be, every edge has to be there. So 1 and 4 are actually connected to each other, not directly, but you can go from 1 to 2 and 2 to 4. So you think of the graph as allowing, graph as like these vertices are intersections and these edges as streets. So if you can go from, can you go from 1 to 4? Yes, you can go from 1 to 3 and then 3 to 4. So that is how you can go, but you cannot go from 1 to 5. So it is disconnected. Whereas these graphs are connected. You can go from any vertex to any vertex. So I hope the notion of connected is clear. So that's what connected means. I will not write it. Connected means you can go from any vertex to any vertex by hopping to neighbors. Neighbor is a edge. Neighbor is a other end of an edge. So like if you are connected directly by an edge, it's a neighbor. So 1 and 2 are neighbors. So you can go from 1 to 2 and 2 to 4. So 1 and 4 are connected. So what a tree is a connected graph, but it should have no cycles. What is a cycle? Here we can go from 1 to 2, 2 to 3 and 3 to 1. That is a cycle. Okay. So cycle is a collection of vertices, distinct vertices, which come back, except the first and last, they are distinct. 1, 2, 3 and 1 is a cycle. 1 to 1 is not a cycle. Okay. Or 1, 2, 3, 2, 1 is not a cycle. But 1, 2, 3, 1 is a cycle. 2, 3, 4, 2 is a cycle. So a graph, this graph is neither connected nor, and it does have cycles. So what is a connected graph without cycles? So if you try to draw them, you will see, so they look like, so a connected graph without cycles, how does it look? So for example, maybe vertex 1 is connected to vertex 2, is connected to vertex 3, maybe vertex 4 is connected to this, and 5, 6. So this is an example of a tree. Okay, so this is an example of a tree where, which is a labeled. Okay, so we are also considering labels. So where the vertices are labeled by 1 to n. Okay, so that's how we will consider. Anyway, this is a tree because it is connected. You can go from anywhere to anywhere. And it is, there are no cycles. You cannot, unless you come back, you cannot come back. I mean, you have to retrace your path to come back to the same point. Now, in this same one, if I had something like this, so this would not be a tree because it is disconnected. Such a thing is called a forest because a forest is a collection of trees. So this is not a tree, but if this was connected to something else, let us say there is an edge between 2 and 8, then this is indeed a tree. Okay, so this is a tree. So this is the kind of object we are counting. So I hope, is it clear what is the objects we are counting? We are counting trees which are connected graphs with no cycles, and the vertices are 1 to n. Okay, so that is the object, that is the collection of objects that we want to count. Are there any questions at this point? So I cannot see if anybody puts anything on chat. Then, yeah, maybe the organizers can tell me.
Yeah, I will let you know. Till now,
Okay.
everything
Okay.
from the-
Okay, so the problem is to count the number of connected graphs with no cycles on the vertex set 1, 2, 3 up to n. So let's do the example. So let's do one more example so that it is clear. So, so let us take n equal to 3. What are all the trees with vertex set 3? That is 1, 2, and 3. Well, as you can see, there is not much choice. Actually, there is only one kind of tree. Basically, if you look at it, without labeling, this is the only kind of tree that you will have. That's the point. So in counting again, I want to emphasize what we consider same, what we consider as different are important. So if you consider unlabeled trees, there is only one. There is nothing else. However, we are labeling them. So this is one tree. This is another tree. And this is yet another tree. Okay. So this is what a tree. These are all the trees. So there are 3 trees. 3 trees with the vertex label 1, 2, 3. Okay. So that's the what we are counting. And this says that the Cayley's theorem says it is n to the n minus 2. So when n is 3, it is 3 to the power of 3 minus 2, which is 1. But that is 3 to the power of 1, which is 3. So this agrees with that formula for n equal to 3. But it gets more complicated when n is 4. So when n is 4, what happens? So when n is 4, there are lots of trees. I will not write all of them. So there are 16 trees according to Cayley's formula. So for example, so this is an example of a tree. Whereas this would be a different tree. And this is yet another tree. Oh, sorry. 1, 2, 3. So I made a mistake. Yes. So this is, so if I put 1 here and let's say 2, 3, 4, this is a different tree. Whereas if I put 2 here and 1, 3, and 4, that's yet another tree. Okay. However, as I said, what matters are it said. So if I put 1 here and put it in a different order, you might say if I put 2, 4, and 3, it's different. No, this is actually same as this. So I should not count it differently from this. These two are the same. 1 is in the middle and it is connected to 2, 3, and 4. That's the same in both cases. The collection is the same. So one way to be sure is the following. So I hope this is clear. So the problem is of counting. But before that, let me say how to keep track of whether it's same or not. There is a standard way to encode a graph. For example, to put it on a computer, you just write down what is called the adjacency matrix. So for example, the adjacency matrix is which we will use later. So what is the adjacency matrix? So you can capture this edge information. So the vertices you write as rows and columns. 1, 2, 3, and 4 in this case. So 1, 2, 3, and 4. So let us do it for this particular tree. So how do I keep track of the adjacency information? I put a 1 wherever there is an edge. 1 and 2 are connected, so I put a 1 here. 1 and 3 are not connected. So 1 is not connected to anything else. Those are zeros. Now 2 is connected to 1 and 3 and 4. So it has 1 on all these places. 2 to 2 is 0. Whereas 3 is connected to 2. So you have a 1 here and a 0 in these places. And whereas 4 is connected to 2. Sorry. So here is the 1. Four is connected to 2 and then not to anything else. So this is the adjacency matrix. Okay, the adjacency matrix of this particular graph. It is always a symmetric matrix with the entries being zeros and ones. So this way you can make sure that two graphs are identical. First of all, you should write the vertices in the order 1, 2, 3, 4. So if you have two labeled graphs, two graphs whose vertices are labeled 1 to n, then you write the adjacency matrix, then you will immediately know whether they are same or not. The drawing pictures, one can be confused whether they are same, whether they are different. Maybe they don't look same, but they're actually the same. So if you write the adjacency matrix, you will know whether or not they are the same. In fact, adjacency matrix completely determines whether the graph. Okay. So that's a useful tool to code it, to write down all the things. Okay, so with that, now let me come to this counting question. How on earth are we going to count? So how do we do counting problems? There are many counting problems you may have done. It's always a tricky thing to do counting. So you can always undercount, overcount, etc. So how do we do such a counting? So there are many proofs of Cayley's theorem. I wanted to explain one in detail and maybe mention a few others. So there are many proofs actually. Okay, so let me just do a kind of quick survey of what kinds of proofs there can be, and then we will talk about one of them and maybe if time permits one more. Okay, so the most nicest way there's okay. So one of the ways is like, I mean, if you could write down all of them and count, that would be one thing. But here it seems a bit tricky. You have to how they can be connected, how to identify two of them. Even for 4, it's a good exercise to write down all trees with vertex set 1, 2, 3, 4. There are 16 of them, and make sure you get them right. So one of the ways is standard method in combinatorics, a very good way of thinking is always to make a bijection with a set that you already know. Now here, at least we have been told the answer. Okay, it's another matter if we don't know the answer, that is a harder issue. But suppose we already are told the answer and our job is only proving it. Then one of the natural ways is to see, okay, what does this count? Can you think of any set which is counted by this number and try to make a bijection with that? That would be one very nice approach. And that is, in fact, one approach. So to make a bijection, but what, so can anybody say what is counted by this n to the n minus 2? What is a natural set that is counted by n to the n? Whose number is n to the n minus 2? Then we can try to make a bijection between trees and that collection. Yeah, anyone? So since I don't know the audience, I'm just throwing a question here. So
I don't see any question now.
no, I mean, I didn't mean a question. I am asking a question. So I didn't know. I don't know if anybody wants to answer. So I'm asking what is, so we want to show number of labeled trees on n vertices 1 to n is n to the n minus 2. I'm asking what is a set which is naturally counted by n to the n minus 2. So n to the power n minus 2 is the number of tuples xn minus 2 such that 1 less than equal to xi less than equal to n integers. So you look at all n minus 2 tuples of numbers coming from 1 to n. That number is exactly n to the n minus 2, right? So this is the simplest set which is counted by n to the n minus 2. Another way to write this set is also, if you like, if you prefer, you can say it is the set of all functions. Well, okay. Yeah, so right. Maybe I'll remove this for a moment. So n to the n minus 2 is the number of such tuples 1 to n, x1, x2, xn minus 2, where each xi is between 1 to n and they can be equal. Okay. So is there natural bijection? So set up a bijection between, let's call it Tn, which is the set of labeled trees, set of trees with vertices 1 to n, and this set, okay, the set of this set. I'll just write this set, I mean this one, set of tuples. Is there a way to make a bijection? This is actually one of the most natural proofs. What I want to spend time on in this talk is not this proof, but I will just tell you there is indeed a proof like this. I will not give you the details, but I will tell you what is the way to set up a bijection, because this is a very beautiful and important object. So this is called proof for coding. I will just show you by example and then leave all the details to you, because in this kind of talk, I feel that a lot of things should be left open so that anybody interested has more to read. There is another proof which I will go over in more detail, another approach which I will go over in more detail. I don't know how much details of all of them I'll give. So what is this coding, that proof for coding, which will set up a bijection between. So let's take an example of a tree and I will just show you how to convert it to a sequence. So bijection means if you take a tree, I have to give you a tuple, and if I give you a tuple, I have to give you a tree in such a way that they are inverses of each other. Okay, so let us see what is a, so suppose I take a tree. So let's just write down a tree. So maybe the vertices are labeled 1, 2, 3, 4, 5, 6, and 7. Okay. So I want to convert this into a sequence. Okay. So this is the proof for coding. Okay. So into a sequence. So what is the, so I will only describe this in words. I hope it will be clear. I will be happy to repeat it if it is not clear. So the way to convert it into a sequence is the following. You look at the lowest leaf. Leaf is a vertex of degree 1. Okay, so a hanging vertex. So a vertex which has only one edge coming out of it in a tree is called a leaf. So 1, 2, 5, and 7 are leaves here. Okay, so you start with the leaf with the lowest label. Okay, so this is the leaf with the lowest label, and see what is it connected to, and you write down that number 3. Okay, so that is the first element of my sequence. Now what is the second element of my sequence? I kind of, so maybe I will use a highlighter to do the deletion. So I will now delete this entire piece. Okay, so I delete this. So imagine that I don't want to delete because I want the tree to remain at the end. I don't want to erase it, but imagine that 1 and the edge connecting to 3 have been removed. So now you have a smaller tree and you just proceed in exactly the same fashion. Okay, so now you have a smaller tree. It's not labeled by 1 to n, but it is labeled by distinct labels. Always go to the leaf with the lowest label and see what is it connected to. In this case, it is the leaf is 2 and it is connected to 6. So we write down 6 and then we delete that particular edge. Okay, so now we have a reduced tree. Now we have a reduced tree with only 5 vertices. Now what is the lowest label? Leaf. Now 3 is a leaf. Remember, originally 3 was not a leaf because 3 has 2 edges coming out, but now that it has been deleted, 3 is actually a leaf. and it is connected to the edge 4. So, connected to the vertex 4. So the next one is this 4. So I am deleting this edge. So this is the third edge to be deleted. Now I have 4, 6, 5 and 7 left. The leaf with the smallest label, 5 and 7 are the only leaves, and the leaf with the smallest label is 5. It is connected to 6. So we deleted this label, this edge. I should have written in what order. Okay, I deleted, but it's okay. Anyway, so I got down 6 here. Now we have 3 things. 6, 4, 7. 2 leaves are there. 6 and 7. Remember, all these edges are deleted. 6, 4, 7. 6 and 7 are leaves. And of this, the lowest leaf is 6 and it is connected to 4. Okay, so we delete that one. Now, once you reach once you reach a single edge, you stop. Okay, now you are left with a single edge 4, 7. There is a leaf, both are leaves, of course, 4 and 7. You could delete 4, but we don't. We just stop here. So we get there were n vertices, we got n minus 2 length here. So 1 to 7 and we got 5 here. So this is the proof for coding. So for this tree, the proof for code is given by this. Okay, the claim is you can go back. So if you know this proof of code and you know the algorithm, you can go back. Okay, for example, you can tell which are the leaves, original leaves, because they don't appear here. For example, 1, 2, 5 and 7 don't appear here. So they must have been leaves in the original. In fact, you can reverse this, but I will not try to explain what is the, you can reverse this, that is the inverse map. So this is actually a bijection. Now, if you accept that this is a bijection, then it is immediate that this is n to the n minus 2. Okay, so this is n to the n minus 2, and you get coding of the tree. So this is one of the nicest proofs. This is and an important one. This is a good coding of the tree, and it is also possible to, any questions here about this coding?
Yes, sir.
Yeah,
Uh,
please.
I have a question regarding the reverse map. So there is no information about the original leaves. So they can be placed interchangeably, right?
Not really, because you remember the rule is that always the lowest labeled leaf is going to be, that is how we work with. So for example, if you were to try to reconstruct here, 1 has not appeared. So you agree 1 is a leaf, right?
Yeah, yeah.
So 1 must be a leaf. And what is it connected to? It would be the first one to be removed. So it must be connected to 3.
Okay.
So just looking at it, I can say that 1 is connected to 3. Okay. So next, the next leaf is connected to 6. So it must have been 2. 2 does not appear. 2 is a leaf. So 2 must be connected to 6.
Yeah.
Okay. Next 3. So the third, so something is connected to 4. Okay. So what is the lowest labeled vertex that is there, which is not yet, so 4 is something it has to be connected to by what? Now it is 3. Okay. So this is how you can reconstruct because 3 is the lowest labeled one that has not yet been attached. So that is you can go back actually. So
Okay.
I'm not giving the full details. So next 5 is a leaf, 5 is, so 6 comes. So it has to be 5 which is connected to 6, and then you can reconstruct back and you will get back the tree. Okay, so this is how it will proceed.
Okay, sir.
So we have to remember that always the lowest labeled leaf is the one that is removed, and we write down what is. So this is a bijection. There are other bijective proofs with slight differences. So for just so that people can look up, there are things like Joel's bijection and Pittman's bijection. Okay. So there is a famous book called Proofs from the Book. It's a book with a lot of interesting theorems with very elegant proofs. There, this topic is discussed, and this Pitman's projection, Joel's projection are described, if I remember correctly. So this is a long time ago. I think this theorem is there and described. So this is one approach to the proof of Cayley's theorem. Okay, but I want to talk about some other things which proofs are. What is it good for? I mean, so if we have one proof, isn't that enough? Do I need another proof? In mathematics, we are not looking for proof for the sake of just verifying whether something is true or false. Now, that is one function of a proof, to say is this statement true or is it false. For that, one proof is sufficient, but that's not the intention of proofs. Proofs illuminate many things. Okay, so for example, proof can allow you to do more things. So one of the things that is interesting is to take, for example, a random tree. So there are however many trees, according to this, there are n to the n minus 2 trees. So suppose I pick one of them at random. Okay. So what is the number of leaves it will have? What is the expected number of leaves it will have? What is the expected distance between, what is the structure of the tree? If you ask such questions, certain things will be answered well by the coding. So when you code a tree by a tuple, it's an entirely different looking object. So some features of the tree are well preserved in the coding. Some features are not well preserved. For example, if I ask you how many leaves are there in this tree, by just looking at the coding, you can immediately tell, because it is all those numbers which did not appear here, 1, 2, 5, and 7. They didn't appear, so those are the leaves of the original tree. However, if I ask you what is the distance between 1 and 2 in the original tree, distance means 1 to 2, how many steps do I have to take? 1, 2, 3, and 4. 4 steps. That is not actually visible from this coding. So that's why different proofs are useful for different purposes. So let me tell you a completely different approach, which is via somewhat linear algebraic. So this is matrix tree theorem. Okay, so it's something more powerful. It does something more powerful, okay, than the original problem. So and it's extremely beautiful. So let me explain the theorem and then we will see. So take any graph G. So G is any graph. A finite graph. Okay. So let's write an example. It could be something like this. Okay. So and vertices are labeled by some numbers 1, 2, 3, 4, 5, 6, and 7. Okay. So suppose this is a finite graph. So here what this matrix tree theorem does is something of a a spanning tree. Is a subgraph of G. Subgraph of G means you choose a subset of vertices and edges, but here I say spanning, so containing all vertices. I need to keep all vertices. And I did not say this before, there have to be n minus 1 edges. Okay, so and is a tree. So that's equivalent to saying connected and so it's you have to have all the vertices and only n edges. And it is a tree. So for example, in this this is a spanning tree. So 1, 2, 5, 6, 3, 4, 7. So this is a spanning tree. Okay. So there are many spanning trees. So here is another spanning tree. I hope it is clear. This is also a spanning tree. So these are spanning trees. Okay. So this other approach counts the number of spanning trees of any graph. Okay. So if the graph is the complete graph, if G is Kn, then Kn is the matrix, is the graph where everything is connected to everything else. So this is the complete graph. Okay, complete graph. So then trees, spanning trees are precisely trees with label 1 to n. So the original thing that I was counting is a special case of this counting spanning trees of a graph, because if we take the complete graph, then we get all trees, because in a complete graph, all edges are there. There is no restriction. It doesn't say you can't connect 1 to 7. You can. So whereas in this graph, I cannot put an edge 1 to 6. It's not there in the graph, right? So when we take the complete graph, we get the original problem. And it's a very famous theorem of Kirchhoff physicist. So before I describe it, I have to tell you how we study it. So before I tell the theorem, I have to tell you. So earlier I described for you the adjacency matrix of a graph. Okay. So first, now we need to define a new matrix called the Laplacian matrix of a graph. Laplacian of G, it is an n cross n matrix. Okay. It's like the adjacency matrix. Okay, it is much like the adjacency matrix. So let's take this example. Let's work with this one. So what is the adjacency matrix of this? So adjacency matrix puts, so we have 1, 2, I just for my own convenience, I'll write 1, 2, 3, 4, and oh, okay, there are too many here. 5, 6, 7. So there are 7, it's too big. So let me write part of it maybe. So there are edges. Where are the edges? Between 1 and 2, there is an edge. Between 1 and 5, there is an edge. 1. So if I put 1, 2, 3, 4, 5, 6, 7, between 1 and 2, there is an edge. And between 1 and 5, there is an edge. In the Laplacian matrix, we make those things -1. Okay. And these are 0. Whereas 2 is connected to 1, 6, and 3. So we put a -1 here, 6 and 3. So -1 there. Okay. And the rest of the off-diagonal entries are 0. I'll come to the diagonal entries. So I'll just write for 3. For 3 is connected to 2, 6, 4, and 7. So when we come to the third row, it has a -1 here, -1 here, -1 here, and -1 here. And there is 0 for these two. Now, what is on the diagonal? Okay, I hope the description of the off-diagonal entries are clear. On the diagonal, we put the degree, that is how many edges are coming out. So for 1, it is 2, because 2 edges are coming out of 1, which is just the row sums may make it 0. That's all. Here, 3, because the row sum will be 0. So 2 is connected to 3 things, it is 3, and 3 is connected to 4 things, so it is 4 here. So whatever is so for the fifth one, it will be again 3 here, because 5 is connected to 3, and then 5 will have -1 at 1, 6, and 7. So -1, -1, -1, and zeros here, and so on. Okay, this is called the Laplacian matrix. Now, this is an important one. So this is called the Laplacian of the graph. It's very closely related to the adjacency matrix, clearly. Off diagonals are basically negative of the adjacency matrix. On the diagonal, we have degrees. So now with this, we can now state Kirchhoff's theorem, which is a very beautiful theorem. the number of spanning trees of G is equal to, so first let me write determinant of LG. This can't be true. Why? So something is wrong if I state the theorem like this. Can anybody say what is wrong with this? So what are the row sums of LG? It is 0. So if you add each row, so that is if you sum all the columns, you get 0 because each row sum is 0. So the LG is actually a singular matrix. So the determinant would be 0. Okay, so it cannot possibly be equal to determinant of LG. So, but it is of a very related matrix, LG tilde. What is LG tilde? You just remove any one row and one column. Actually, it doesn't have to be the same row, same column. Is LG after removing one row and one column. For example, you can remove the last row and last column and take this as LG tilde. Now, it's a fact that it will not matter which row and which column I remove. So that's a good exercise in linear algebra. Why it shouldn't matter? The determinant will give me the same answer. Whichever the original one has determinant 0, and whichever row and whichever column you remove, you get the same determinant. And Kirchhoff's theorem tells you that this determinant is actually the number of spanning trees, which is remarkable because if you know the determinant is originally we see it in the context of solving linear equations. So the determinant helps you to tell whether a linear system is solvable or not. And then later we find miraculously that it is also useful for counting volumes. So the volume of a parallelepiped is given by the determinant of the column vectors given by its sides. But here is a completely stunning application of determinant that it is helping you to count something. Okay, the determinant of an appropriate matrix helps to count something. So how is this useful? Let's do the special case of the complete graph. Let's come to the complete graph. G equal to Kn, complete graph. So in this case, what is LG? So this is the corollary to Kirchhoff's theorem. So what is the Laplacian matrix? So there are n vertices. So each vertex is connected to all the others. So the degrees are n minus 1, dot, dot, dot. And every vertex is connected to everything else. So all the off-diagonal entries are minus 1, minus 1, minus 1. Both upper and lower side. It's a symmetric matrix. Okay, so this is the Laplacian matrix, and as before, if you take the row sums and column sums, you get 0, so that is fine. So that will be a singular matrix. So now let's take LG tilde, which is you remove the last row and last column. Remove last row and last column. You can remove any row and any column. It's just easier if you remove the same row and same column in this case. So what is LG tilde now? What will be LG tilde? So this is an n cross n matrix. LG tilde looks exactly the same, but it's an n minus 1 cross n minus 1 matrix. And minus 1s here, but it is an n minus 1 cross n minus 1 matrix, which if you like, you can write it as n times identity n minus 1 minus the all 1 matrix. This is the all 1 matrix. Which is actually a rank 1 matrix. You can write it as 1, 1 transpose. You take the vector of 1s and take 1 into 1 transpose, you will get Jn minus 1. Okay. So this is this. So what is LG tilde? How do I find its determinant? Well, you can directly find the determinant, but you might as well find you can even find the eigenvalues. because Jn minus 1 is a rank 1 matrix, it has two eigenvalues. So Jn minus 1 eigenvalues are n minus 1 and all the rest are 0 because it is rank 1 matrix. All the other eigenvalues are n minus 2 zeros. Now, when I take n times identity, the eigenvalues are n and n, and I subtract. So the eigenvalues of this LG tilde are n minus the eigenvalues because we are shifting by identity. So it will be 1. N minus of n minus n is 1, and the rest are n, 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 n. How many of them? N minus 2 of them. So the determinant of LG tilde will be the product of eigenvalues, which is n raised to the power of n minus 2. This is Cayley's theorem. Okay, so this Kirchhoff's theorem is a much more general theorem which gives you Cayley's theorem. It's extraordinarily powerful, actually. It can be used for many things. So, I don't have time. I'm already at 12:52, so I have 10 minutes, so I will not go through it. But using this, one can find many things. You can also apply it to other graphs. But you can also find what is the distance between 1 and 2 in the graph. In the complete graph, when I take a random tree, what is the distance between 1 and 2? Two vertices. Okay, so one can study all that using Kirchhoff's theorem. So I will not give you a proof, but only a very light proof sketch. Proof sketch is that LG can be written in the following form. LG can be written as B transpose. Okay. What is the matrix B? B is like this. The number of things is here. It is the vertices. The rows are labeled by vertices. The columns are labeled by edges. Okay. So what we have to do is, if you have a graph, what you do is this is a signed, I will write signed vertex edge adjacency matrix. What it means is, for each edge, so let's say E1 is an edge. So there will be two endpoints to it. So one of them will be marked 1 and the other will be marked -1. To each edge, you decide whichever way you want. You put a +1 in one place and -1 in another place. All others are 0. Every edge has two vertices, right? So for any edge, E7 will be connected. It will be connecting two vertices. One of them you make +1, one of them you make -1. Okay, and like this. So you fill this matrix. It's a signed vertex edge adjacency matrix. It's telling you which vertices are adjacent to which edges, but there is an arbitrary plus minus chosen here. Then you can check that B times B dagger will give you exactly the Laplacian matrix as I defined it here. And what you need to do now is, how do I do the determinant of a product of two rectangular matrix times its transpose? How do I do that? There is a famous identity called Cauchy-Binet, which says that determinant of B dagger is, this is a rectangular matrix, okay? But it is the sum of it's not determinant B into determinant B dagger. That doesn't make sense because B is not a square matrix. But what you do is you pick any number of columns which is equal to the number of rows, so that you get a square matrix. So you take any subset of edges with the same number of elements as the vertex set. So you get a square matrix, that is what I call BS. B sub S is you take the columns corresponding to the subset S. And then that's a square matrix. You can find its determinant, you can square it. And that Cauchy-Binet tells you it is this. So what happens here in the particular situation at hand is this is 0 or 1, depending on whether S is a subset of edges, right? So, well, okay, sorry, I should not have done, I should have removed one row because we have to go to LG tilde. I made a mistake. So we have to remove one row and one column, but the same thing is true. If you just take this part, B, if this part is B, then the corresponding B, if we call this B tilde, LG tilde will be B tilde transpose. And those will give me zeros or ones depending on whether we have a spanning tree or not. But I don't want to explain. But anyway, now that you know the names, you can probably look up the proofs and in detail. So do I have a couple of minutes or should I stop for questions now?
You can take some more time. Anyway, next up will start at 2. So.
Okay. So in that case, I will just end with another description because I am not giving detailed proofs. As I said, it's fine. As long as you know the words, you can look up the proofs, and the proofs are not super difficult, but the ideas are beautiful and they are useful for studying. Okay, so this matrix tree theorem, I mean, this is what Kirchhoff's theorem is actually. That's what I meant by the matrix. But there is a completely different approach, also different looking approach, which is how do I pick one of these at random? Okay, so that is an important thing in probability. There is a finite set, namely the set of trees of all trees or the set of spanning trees of a given graph. So how to pick a at random, uniform probability. So there it turns out that this will give another proof of Cayley's theorem. If you give so it turns out there is a very beautiful algorithm. There are multiple ones. One of them is called the Aldous-Broder algorithm. Which again, it is easier to describe in, okay, actually I have a mathematical code. First, let me describe and I will show you. So I have here, can you see this screen?
Yes, you can.
Okay. So, okay. So let me describe, first let me describe here in words. So you have a graph, okay? Oh, I have a graph here. A random walk is starting somewhere, okay? A random walk starts somewhere and then it goes to one of the neighbors with equal probability. If you start at 2, next maybe you go to 6, 3 or 1. Suppose you come to 6. Then you go to 5 or 3 or 2. And then let's say you come to 5. Now you can go to 1 or 7 or 6. So maybe you go back to 6, then to 3, then to 7, then to 5, then to 1, then to 2, and so on. So a random walk is just at each point you toss the coins to decide and choose among your neighbors with equal probability and go to the neighbor, one of the chosen neighbor. And how do you make a tree out of it? So here is an example of a graph. Here is, okay, let me run this. What happened here? Something is wrong. Okay. So what I did here is I did on a complete graph. So complete graph is not pictured here, but this is the random walk. It starts at vertex 1, then goes to 6, then goes to 10, goes to 2, goes to 4, 8, 2, 8, 2, 9, and so on. And what we have to see is Aldous-Broder algorithm, I'll describe in words, is this. Look at the first time any vertex. So look at the first time any vertex is visited, except one. One is visited the very first time. So you have to look at. So you have to look at the first time vertex 2 is visited. Vertex 2 is visited via vertex 10. Okay, so 10 to 2. Okay, and vertex 3, when is the first time vertex 3 comes? It is visited from 9. Vertex 4 comes here first time, it is visited from 2. So you just, for each vertex other than 1, you see where did you visit it first time and from where. So 10 to 2, 9 to 3, 2 to 4, 7 to 5. So here is 7 to 5 and 1 to 6. So first time 6 was visited was second step, 1 to 6. So you take this collection of edges and make a tree. So that is your tree. Okay, so I have put here edges 10 to 2. Where is 10 to 2? 10 to 2, 9 to 3, 9 to 3, and 2 to 4, etc. This forms a tree, and it is equal probability that it is any of the spanning trees. So that is what the Aldous border algorithm tells you. Okay, so, and it can be used for counting, but it can be used for much more, studying this random tree actually. But okay, so I should stop somewhere. So this is one algorithm for generating a random tree. Actually, the proof of coding also gives an algorithm for generating random tree, but some features are not so clear in that. Okay. Anyway, I'll stop here. Thanks for your attention.
Thank you, sir. Such a stop. Is there any question? Take 1 or 2 more minutes for the questions.
I had a question.
Uh-huh.
Are there any features of adjacency matrix that we can employ to identify whether the following is a tree or not?
Well, yeah. Well, the connectedness is hard to see from adjacency matrix, but it should have exactly n-1 edges. That is, a tree with n vertices should have exactly n-1 edges. So that's not hard to see. I didn't explain that point, but if you have n vertices, you should have n-1 edges. From the adjacency matrix, you can quickly see how many ones are there on the upper part of the matrix. That should be n-1, but for all you know, it could be disconnected. And there may be a cycle. So it may be disconnected and have a cycle somewhere. So connectedness is not easy to see from the, it's not easy to see immediately from the adjacency matrix. But what from this matrix tree theorem, kind of you can see that, because what happens, for example, so sometimes this determinant LG tilde can be 0. So for a tree, so suppose I have a tree itself. You're asking whether I can see whether it is a tree from the adjacency matrix. From adjacency, you can go to Laplacian matrix, for example. And then suppose I start with, if G is itself a tree, what should be the number of spanning trees of G? It should be 1. There is only one spanning tree. So if I take determinant of LG tilde, it should give me 1. So that is one way to check. If you have the adjacency matrix given to you, go to the Laplacian matrix, remove 1 row, 1 column, compute the determinant. If it is 1, then you started with a tree.
Okay.
Otherwise, it is not.
Okay.
Okay. Any other questions?
Take 1 more minute.
Yeah. Yes.
So I was saying maybe we can take 1 more minute.
Oh, okay. Okay. Sure.
Aldous border algorithm, it's the same that was described in the Remco's book, volume 1, right?
Probably it is described. I do not know. I mean, I don't remember at the moment, but it might be. It is described in many books. There are different algorithms. Another one called Wilson's algorithm is also there.
Yeah, that loop is random walk, that one.
Yeah, exactly. So that is also using random walk. So it's actually miraculous. I mean, so this will give a tree is okay, but it gives equal probability to all trees is quite surprising. That comes from something called the Markov chain tree theorem. So there is a way to do a Markov chain on the space of spanning trees together with a Markov chain on with the simple random walk on the underlying graph. So that is the way one proves these things. But yes, These are probably it is described. It's also there in the book of Lyons and Pegas, Probability on Trees and Networks. Both Wilson's
Right.
algorithm and Aldersborder algorithm are explained. Yeah. Yes.
In the Markov chain, you told me that so from one tree to another tree, you how do you go? So you exchange edge or
Right. So how, I mean, it is simultaneously, there is this Markov chain, which is on rooted trees, rooted subtrees of the graph. Okay.
okay?
So maybe at the moment you are in this subtree, but it is also rooted that one vertex is distinguished.
Yeah.
Okay. So now this is on the underlying graph. I have not written fully. There are other edges. So this one makes a step in the underlying graph. Maybe there is an edge here in the underlying graph. So now the root shifts to here. But now if I put this edge, I will create a cycle. So what you do is you delete so this cycle is created, you delete the next edge, which is this one, and add this edge.
Okay.
And now this is no longer the root. So you went from one rooted tree. Okay, sorry, I destroyed that. But you went from one rooted tree to another rooted tree. This is one step of the Markov chain. And now this root again makes a random walk step. Maybe it will come here. If it comes here, it creates this cycle. It will necessarily create a cycle if you add this edge. So you delete the next one, next edge. If you delete this one, now you have another tree. Now the root has shifted to here. So
Yeah,
that's how,
I get it.
yeah. So you can show that this random walk is uniform distribution. I mean, this stationary distribution of this is uniform on the collection of all rooted trees, rooted spanning trees. And from
I
there,
see.
you can deduce this Aldersborder algorithm. Yeah. Aldersborder is kind of not starting in stationary, it is starting with empty set, but it still works. Yeah.
So do you know mixing times of such chain?
Oh, the mixing time. No, I mean, this
Oh,
one is for
just cut off
exact
of
sampling. No, this
Yeah.
one, this Markov chain is actually, we are not, it's a good question how long it takes. It's an algorithmic question. But you see, this is a Markov chain which gives you exact way to sample a
Yeah,
spanning tree.
yeah.
This is
Sure,
an
sure.
exact sampling algorithm.
Monte Carlo will
Yeah, it's not a Markov chain Monte Carlo method. It is a method where you start from with a graph, you give an actual tree. But how many steps does it take? I think it takes, if at least complete graph, it will take n cube steps, I think. You have to visit all the vertices once. Okay, so what happens is how long does it take till you visit all the vertices? The random walk has to run at least that many steps, right?
yeah. Okay.
And if there are n vertices, it will take n log n steps to visit all the vertices. So in the complete graph, it works quite fast. From the first n log n, that's a coupon collector problem. In the first n log n steps, you can get all the vertices, and then you have to see, but you still have to search and see which was the edge, yeah. But on general graphs, I think it can take up to n cube or something like that. I forget the algorithmic aspect of it. It's not the mixing time question, but the algorithmic question. How long does this algorithm take to run?
Thank you, sir, for such a wonderful talk. If there is there any other question? Okay. There is no. You can stop.
Yeah. Okay.
Thank you.
Thank
Thank
you.
you everyone for
Thank
joining.
you. Yeah, thank you. And have fun. There are many more interesting talks lined up. I saw your program. Enjoy.
See you. Thank you.
Bye.
For participant, the next talk will be at 2. Please join by the link.